All right, so welcome back, everybody. Today we are going over Unit 2, Lesson 3, which will be binomial random variables, continuous variables, and then the normal distribution. And this is what the normal distribution looks like. I just have a picture for you right here. And that's a very important graph to like familiarize yourself with because it's going to be important in this lesson and all of our future lessons. So let's go to the definitions. The first one we have is binomial random variable. And there's 4 requirements that make a variable binomial random variable. So the first one is a finite number of trials, so a number of trials that you can identify. The second one is 2 outcomes, so that means you either have a success or a failure, and you can identify those within the context of the problem, but there's exactly 2 outcomes. That's the important thing there. The third requirement is that each trial is independent of every other trial. The fourth requirement is that the probability of success stays constant throughout all of the trials. Okay, number 15. When x is binomial random variable, our expected value, or our mean, so that's our mu and mean, same thing, that equals n, which is, so n equals number of trials, and then our p is our probability of success. Prob of success. Okay, and so for our standard deviation here, now we are going to say the square root of np times 1 minus p. That's our formula for standard deviation. Okay, the next one, the probability of observing exactly k successes in independent trials is this formula right here. So this is saying the probability that x equals k, so k is successes, and then this term right here would be n combination k, or n choose k, and it would look something like this. And you don't really need to worry about that because you have a button on your calculator that can tell you how to do n choose k. So that's the important thing there, is that you know how to type that in your calculator. And then we would have our p, probability of success, raised to the k. And remember, k is our number of successes. And then we would have 1 minus p to the n minus k. And so n is our number of trials. Okay, and for the last one, this is our normal distribution, and like I said earlier, this is very important. And so let's see. So a normal distribution is a continuous distribution that has the shape of a bell curve. And you can see here that we have about a bell curve, right? And it sort of looks like that because it has the mean is in the middle, and then it funnels down on the outsides. So an important thing here is that we come in here and we see the mean is in the middle, and then if we go 1 standard deviation to the right, it's there, and 1 standard deviation to the left is there. And so our notation, so this sigma is standard deviation. So that means we would have mu plus 1 standard deviation and mu minus 1 standard deviation. And as I wrote here, this is equal to 68% of the total data. And this is symmetric, right? And so that means that we would have, if you take the middle, we would have 50% on this side, and we'd have 50% on this side of it. So 50% to the right of the middle and 50% to the left of the middle. And again, the mean is the expected value, and that is in the middle of our normal curve. And so we have 1 standard deviation to the right, 1 standard deviation to the left, and this is our empirical rule. So that would be that 68% is right here. So 68% is within 1 standard deviation. 95% is within 2 standard deviations. And so that would be our yellow area plus our blue area is 95% of the data. And then 99.7% is 3 standard deviations. So that would be our yellow area plus our blue area plus our pink area. And 3 standard deviations to the right, 3 standard deviations to the left. Add all that together and you get 99.7%. Okay, so now let's go work some problems. So we'll come here And the first problem says, identify which of the following variables can be described by a binomial random variable. A, number of phone calls during an hour. And so I copy and pasted our requirements here. So remember, it's finite number of trials, 2 outcomes, each trial is independent, and the probability of success stays constant. So for the first one, number of phone calls during an hour. So we don't have a finite number of trials here, so this automatically fails at the first requirement, because it says during an hour. So you could make 1 phone call during an hour, or you could make 100 phone calls during an hour. We don't know. It doesn't tell us how many trials we're getting here. So that does not describe a binomial random variable. Okay, and for part B, we have number of coin tosses until heads occurs. And again, this fails our first requirement, because we don't know how many coin tosses there will be until heads occurs. So we don't have a finite number of trials. It just says until heads occurs. So that could be 3 trials, that could be 1,000 trials, we don't know. Okay, for part C, number of correct answers on a multiple choice test with 20 questions when guessing, and there are 5 choices for each question. So for the first one, finite number of trials, yes, there is 20 questions, so it passes the first one. 2 outcomes. So you might look at this and say 5 choices for each question. Oh, that's not 2 outcomes, but we're looking for correct answers. So we can either be correct or we can be incorrect. And those are our only 2 outcomes. We can either guess the correct answer or we can guess the incorrect answer. So yes, it does check out that there are only 2 outcomes. And so now each trial is independent. Yes, they're each independent if you're just guessing and none of the questions have anything to do with any of the other questions. So it works for the third requirement. And then for the last one, the probability of success stays constant. And when there are 5 choices for each question and you're guessing the correct answer, your probability of success, which is P, would be 1/5 or 0.2. So that's going to be the same for every question because you're guessing. Now, if you knew the answer to some of the questions, then it would fail that last requirement. But this one says we're guessing, so I'm going to go ahead and put a check mark here that this is a binomial random variable. All right. Part D, number of people that are red-green colorblind in a random selection of 100 people. All right, so finite number of trials, yes, 100 people. 2 outcomes, you either are or are not red-green colorblind. Those are our 2 outcomes, so yes, it checks that one. Each trial is independent. Now, if they do a random selection, so that means each trial is independent, and the probability of success stays constant, yes, because we're just taking it out of the population. So check mark, this is a binomial random variable. All right. You toss a coin 200 times. Find the probability that exactly half of the coin tosses will be heads. Round your answer to 4 digits after the decimal point. So this goes back to our equation we were talking about earlier, where it is probability that x equals k is k is in combination k, p to the k, 1 minus p to the n minus k. And so now we're going to identify what our n is here, what our k is here, what our p is here. So first we'll do our n, and this would be, you toss a coin 200 times, so our n is 200. Our k, we're looking for exactly half of the coin tosses will be heads, so that would be 100 heads. And then our probability of success is 0.5 because it doesn't say anything about it being a biased coin, so we just have to assume it's a fair coin, and you have the same chance of getting heads as you do tails. So now we're looking for a probability that x equals 100 is 200 combination 100, and then p, which is 0.5 to the 100, and then 1 minus 0.5 to the 100. And I already have this answer for us. This is going to be 0.0564. And now you have to remember when you're doing this problem, you need to enter this not as a fraction, but as a combination on your calculator. And your calculator should have a button for that, so no need to worry about the notation that you don't know, but you need to enter it as a combination. And other than that, this is a fairly simple and quick problem. All right, this problem's a little bigger and a little longer. A club with 25 members is voting on a proposal. A group of 6 has decided to vote in favor of the proposal, while each of the rest of the members vote independently with a chance of 47% in favor of the proposal. What are the chances that the proposal will get the majority vote? Round your answer to 4 digits after the decimal point. So, we're going to say, so we need the majority vote, right? So, out of 25 votes, we need 13 yes votes. But they give us more information that a group of 6 has already decided to vote in favor of the proposal. So that means we only have 19 votes left up to a random voting. So 19 left, and we would only need 6 more yeses. Or no, actually we would need 7 more yeses, I'm sorry. So we would need 7 more yeses, right? Because 6 people have already chosen to vote yes. So out of our 19 remaining votes, we need 7 yeses. And so we need the chances that the proposal will get the majority vote. And so to get the majority vote, you could have 7 yeses, you could have 8, 9, 10, 11, 12, all the way up to 19. But to not get the majority vote, you would have to have 6 or less votes. And so our P here, our probability of success, is 0.47, right? Because they have a 47% chance to vote in favor of the proposal. So here, we're going to use our complement rule from a while ago in order to make this problem just a tad bit easier on ourselves. So this would be the probability of 7, so x is greater than or equal to 7, is the probability that x is less than or equal to 6, or is 1 minus that, right? So we have the probability of voting 0 yeses, 1 yes, 2 yes, 3 yes, 4 yes, 5 yes, 6 yes, and then we would take 1 minus that probability to give us the probability of voting 7 or more yeses. So for probability x equals 0, we have 19 combination 0, and then 0.47 to the 0 times 0.53 to the 19. And this is the same thing as saying 0.53 to the 19. And then we would do the same thing for x equals 1 all the way down to x equals 6. And then we'll add all those together. So added together, this equals, let me see here. This is 1. So this equals 0.1316, and then we would go back up here and say 1 minus 0.1316 equals 0.8684. And that problem turns out to not be too hard. The only hard part about this problem is that you have to calculate all of these. You have to calculate x equals 1, 2, 3, 4, 5, 6, and 0. And then you would have to add them all together and then say 1 minus that answer. But other than that, this problem isn't going to be too hard for you. All right, so for the next one, this is where we're working with a continuous variable. And so this graph here, when you're working with a continuous variable, your probability is your area under the curve. And right here it says this is a probability density function. And if you remember, we looked at a probability mass function a while ago, and that was for discrete variables, but this is a continuous variable, so it's called a probability density function. And it's given by this graph below, and so we need to determine these probabilities. So for the first one, it says probability that x equals 1. So when we have a continuous random variable like this, the probability of it equaling a certain number is always going to be 0, right? Because if you're looking at area under the curve at one singular number, you're not going to be able to figure that out because there's no width there when calculating the rectangle of under that curve. So for the first one is 0. For the next one, probability x is less than or equal to 4. And so what I would do here is I would divide this up into this triangle. So we have this whole triangle right here. So it would look like this. So in order to find our area of a triangle, right, we need our height. So this is the same thing as, and if you remember the formula for area of a triangle, it is 1/2 base times height. And so our base here would be 4, and then our height would be 1/6 because of this number right here. So this comes out to 1/3. So that's going to be the probability that x is less than or equal to 4 based on this graph. And for the next one, we have probability that x is between 4 and 7. So if we come back up here and we look, oh, right here, between 4 and 7, we have a square now. And so remember the formula, I guess it's a rectangle. So the formula for area of a rectangle is length times width. And this one would be 3 across, 3 on the width, and then the length would be 1/6. So this simplifies out to 1/2. And for the last one, it says probability that x is greater than 4. And so if you remember, all of our probability in something has to be 1, so we can use our complement rule here and say this is equal to 1 minus probability x is less than or equal to 4, right? Because if we have greater than 4, it would be all this area, and then less than or equal to 4 would be all this area. So 1 minus this answer here equals 1 minus 1/3, and this is just going to be 2/3. So that's the easiest way to do that problem. You could calculate the area of this rectangle and then this triangle and add them together, but I find it easier to just go ahead and use the complement rule. All right, and so this problem is going to be pretty tough. This is a longer problem, and this has to deal with our normal distribution, right? And so I've copied the normal graphs for everything down here, and I just have those on every part of this problem so we can just work with those when we need them. So again, we're going to be using the empirical rule, which is the 68, 95, 99.7 rule. And if you need a refresher on that, you can go back to the beginning of the video with the definitions and look at it again. But I have us drawn the 68, 95, and 99.7 down here. And so it says, in some state, the mean ACT score in mathematics is 22, and the standard deviation is 5. And so if you remember, we would put our mean score here in the middle. So we're going to be working on this left graph for the ACT. So the mean is always in the middle, and then the standard deviation is 5. So in order to go one standard deviation to the right, we would add 5. So this turns into 27. Then we would add 5 again to 32, and then we would add 5 again to 37. And now I know the max ACT score you can get on anything is a 36, but that doesn't matter for this problem. We're just going to look at the numbers as they come out. So, and then to go to the left of the mean, what we would do is we would subtract the standard deviation. So 22 minus 5 is 17, and then 17 minus 5 is 12, and then a 7 there. So now we've fully made out our ACT graph, and so that means that anything between 17 and 27 is going to be 68%, between 12 and 32 is going to be 95%, and then between 7 and 37 is going to be 99.7% of all of our data. So let's do the same thing for the SAT. So the mean SAT score in mathematics is 500. So the mean, remember, right in the middle. And then the standard deviation is 110. So we're going to go ahead and add 110 to each side. It's going to be 610, 720, 830. And then we'll come to the left and subtract 110, 390, 270, and 160. Or, no, hold on, didn't do that right. So it's 390, then 280, and then 170. So we made our graphs. That's the first important part. So now we're going to go and answer all these questions. So part A, what proportion of ACT scores are less than 12? So 12 is right here, and we need to know less than 12. So we're looking for all of this area, all the way down to the left, past 7, all the way down. So in order to find that, we know that if we take in the middle, all of this area to the right of this is 50%. And then if we can add this plus 50%, that will give us the area to the right. And then we would say 1 minus that would give us the area to the left. So 1 minus 50% plus, or I'm going to say 0.5. 1 minus 0.5 plus, then we need to figure out half of this 68 would be 34% here. And then we would say half of our 95% in this. So these two added together would be 47.5%. So 47.5%. So then we would take our 0.5 plus 0.475, and this is 1 minus 0.975, which is the same thing as 0.025. So that's how we would do the first one. And then the second one, we would say, what proportion of SAT scores are greater than 170? So 170 is down here at 3 standard deviations to the left, and we want proportion all the way to the right of 170. So if we want to find, let's find this tail right here, and then let's use the complement. So if we need to find one tail, we would take this 99.7 here, and then we would say 1 minus 99.7, or it should be 0.997, and this is going to be 0.003. So that is both of these tails added together, and then if we divide 0.003 by 2, that gives us 0.0015. So that means this tail over here is going to be 0.0015. So 1 minus that tail gives us everything to the right of that tail, and that is 0.9985. Okay, part C. What proportion of ACT scores are between 7 and 17? So here we need 7 and 17. So now we need to find these two added together. So I'd say, let's try to find the best way to do this. So we know that 50% is on this side. And then we know this is 34%, which is what we found in another problem because we divide 68% by 2 to find that. So now, and we remember this tail right here, which we found in the last problem, is 0.0015. So if we say 50%, so 0.5 minus 0.34 plus 0.0015, this will equal 0.1585. And I would say that's the fastest way to do that. All right, the next part. What proportion of SAT scores are between 170 and 830? So let's see, 170 is right here, 830 is right here. And since this would be 3 standard deviations to the left, so 3 standard deviations and 3 standard deviations there, we already know this rule based on the empirical rule. And then this would just be 0.997, and that comes from right here. That part's easy for us. So now this E, F, and G we'll ask about up here. So Terrence gets a score of 18 on the mathematics proportion of the ACT, and Philip gets a score of 469 on the mathematics portion of the SAT. So now we're going to come down here, and we're going to say Terrence gets an 18 and Philip gets a 469. So Terrence gets in, so our x is going to be 18, and our x is our observed value, so x is 469 here. And then we need to find, so the mu of ACT scores was 22, and the mu of SAT scores was 500. And then our standard deviation of ACT scores was 5, and our standard deviation of SAT scores is 110. So now we're going to use our z-score formula that I have written down here. So this would be z equals 18 minus 22 over 5. And this is going to be 0.8. And this one is 469 minus 500 over 110. And that answer is negative 0.2818, and the 0.8 up here is also negative, so because these are less than the mean, they're less than the expected value, so they're going to be to the left of it, and it's going to end up in a negative z-score. And so who did better in mathematics, Terrence or Philip? So when you look at z-scores, z-score is a way of basically comparing how you did in different things, and then you can compare how well you did versus the standard deviation and versus the mean, and then so that way you can compare two things that aren't the same. So in this case, we're comparing ACT scores with SAT scores, and this would be the best way to do it, is to normalize them and then find the z-score of two different people who took the different tests. So Terrence's z-score was negative 0.8 and Philip's z-score was negative 2.818. And so this would tell us that Philip did better because his z-score has a higher value, right? And negative 2.8 is a higher number than negative 0.8. So he is further up to the right. And the further to the right you can get on this graph, the better that you did. Make sense? Good. So now the only thing we have left for this is an RStudio thing. So I will be back and I will show you the RStudio after this, and it says download this assignment and read the data into R, then create a QQ plot for each of the variables x1, x2, and x3 using this function, which of the three variables is normally distributed. So I'll show you the RStudio stuff now. Alright, so now we are on to the RStudio part. And so what we did here is we got our data into RStudio, and this is our assignment 7 QQ plot. And this is what it looks like, is all these numbers. So the first thing we're going to do is it told us to use the QQ norm function. So we would type QQ norm, open parentheses, and then we're going to tell it what data we want to call. So it would be assignment 7, so it's this. And then we would put a $sign to tell it what variable from the data. And then we want x1. So this is what our QQ normal plot would look like. And then we need to see it with a line on it. So QQ line of this assignment 7 and a $sign to tell it again x1. So now if you can see this line here, it puts a normal line through the data. And what we would really want for a normal variable is not these data points trailing away from the line. So I'm guessing that this is not going to be our correct answer because we can see these down here trail away and we can see these down here trail away. So then we're going to click our up arrow twice to bring back this data. So now we're going to backspace that and say x2. So this is our data for x2. And then we'll go to up arrows again and say x2 there. And so it adds another line, and we can see that, again, there's data points trailing off, so I don't like this one either. So let's do it for the third one now. Okay, this one does look a lot better. We don't have as many points trailing off. So now let's do the line part of it. And, oh, that looks so much better, doesn't it? So we don't have data points trailing off at the end. We have this line running about through the middle of the data the whole way through. So I'm going to say that x3 is the most normally distributed. All right, thank you for watching.